Good morning, good afternoon, good evening class. I'm Mr. Arocena, and today's video we're going to go over a few of the problems from your textbook that are a little more difficult. This is on page 154, so page 154, and I think questions 91 to 93. So let's start with question 91. So here you're asked to find what is the original concentration of NH3. And it tells you that 1.3% of the NH3 dissociates, dissolves, I guess. And then it asks you to calculate also the concentration of hydroxide. So this is, I'll call it the original concentration of NH3 and EQ concentration of OH minus. So what this basically means is that because NH3 is a weak base, it's not a strong base, it'll form an equilibrium and will create the following: NH4 plus OH minus. So we are asked to find the original amount. So let me just arrange my table. Being an equilibrium, we will have to use a Rice table to help us solve this. There's my reaction, initial, change, equilibrium. Okay. And we don't know what the NH3 is, so I will call this X. Okay. As usual, we don't care overly about the water because it's a liquid and that doesn't affect our equilibrium calculations. We don't have any of this. Okay, we don't have any of that. And then now we're asked, it looks like the rest of the table is going to be kind of hard to fill in, but we know this bit. We know this bit. So what we can do here is we can say, okay, this is how much dissolves. So this means then that I'm going to dissolve, I'm going to get this much NH4 plus because 1.3% of the original amount will dissolve into NH4 plus. Now, because of the way the reaction is arranged, this change here, the change here, I guess plus Y, and this change here have to be the same based on the reaction equation. If I know this, so if I know this, and since the OH minus changes by the same amount, I can put that in as well. So this will change by minus Y, but we're going to assume the change is really small, so this will remain X. So X minus Y is going to approximately equal X. All right, where do we go from here? Well, this is a weak base equilibrium, so we can set up the equilibrium equation as follows. Kb is equal to concentration of NH4 plus, so 0.013 X times 0.013x as follows. This will be all over x. Oops, I should x. Now it still looks like we have a variable that's missing, and that's kb, but we can actually calculate that because we know that the kb of NH3 is just going to be the kw over the ka of its conjugate acid, and the conjugate acid of NH3 is NH4 plus, which is in your textbook. Yeah, it should be in your textbook. So kW 1.0 times 10 to the negative 14. Ka, let me just look it up. So the Ka of NH4 is 5.6 times 10 to the negative 10. Yeah, 5.6 times 10 to the negative 10. So just calculate that out quickly. So 1 to the negative 4, 1 times 10 to the negative 14 divided by 5.6 times 10 to the negative 10. So we get an answer of 1.79 times 10 to the negative 5. 1.79 times 10 to the negative 5. That's my KB. Now we'll set that over here. 1.79 times 10 to the negative 5. This will just be 0.013 squared, x squared. This x. Oh, hey, this actually works out really well because this will cancel that out. So we got 1.79 times 10 to the negative 5 equals 0.013 squared x. So we just divide by that. 0 squared, and that will give us our concentration for x. Okay. Calculator, so we'll divide by 0.013, divide 0.013. So x is 0.106 approximately. There's the original concentration of NH3 original. And then for the concentration of hydroxide, it's going to be 0.013 times 0.106 molar, which is 0.013, 0.00137 or 0.0014. Your textbook might write it as 1.4 times 10 to the negative 3 molar. There you go. There. That's how we can. That's how that one is done. Trick, I suppose, here is realizing that the 1.3% dissolving is going to translate into your equilibrium concentration there. All right. Hopefully that helps. Okay, so that's question 91. Let's go on to question 92. I think this was actually an example in one of in the calculations KB video, but let's redo this, hopefully with a little more clarity. All right, so question 92 asks you to calculate the pH of a saturated solution of CaF2, calcium fluoride, and it gives you the KSP value of this as 1.46 times 10 to the negative 10. For this question, you're going to have to do 2 rice tables. One rice table will be for the dissolving of CaF2 into calcium ions and fluoride ions. And this is going to be a solid. And the second rice table will be for the weak, yes, in this case, a weak base. Yeah, because we're talking about KB, a weak base equilibrium. So first, though, we'll start this way. We don't care about this column because it's a solid, doesn't affect our equilibrium calculations. Initially, these start out at 0, then they gain some amount. This will be 2x because of the 2. This will then just become x, and this will be 2x. Now, if you remember from solubility equilibrium, KSP is just going to be the concentration of calcium times the concentration of the fluorine. Because we've got 2 of them, we've got to square that. We'll just put in our value for KSP as 1.46 times 10 to the negative 10. Calcium, the concentration of calcium we don't know, but we gave it a variable x, and then the concentration of the fluoride is 2x, but we've got 2 of them, so we'll go squared. Okay, simplifying things a little bit, we get 1.46 times 10 to the negative 10. This, the 2 will square that, it'll square that, so we get x times 4x squared. Altogether, this becomes 1.46 times 10 to the negative 10, and this will be 4x cubed. All right, some algebra later, we'll divide this by 4, then cube root that. That'll give me x, which will be the concentration of x is the concentration of calcium, 2x is the concentration of fluoride. All right, let's pull out the calculator and we'll put it in. So 1.46 times 10 to the negative 10 divided by 4, and then we'll cube root that. So we get x is 3.317 times 10 to the negative 4. Yeah, negative 4. And then therefore 2x
will be 6.3.317 times 2, so 6.634, 6.634 times 10 to the negative 4. All right, so that's our concentration of fluoride. Now the second equilibrium is going to be the fluoride ions reacting with water to create hydrogen fluoride and OH minus. There's our second equilibrium. And we basically repeat the process, but this time this is a weak base equilibrium, so we're going to use the Kb of F minus as opposed to the Ksp of the calcium fluoride. Reaction, initial change, equilibrium. So our initial amount of F minus is 6.634 times 10 to the negative 4. Water doesn't matter because it's a liquid. HF, original amounts are 0. This will change by some number. This will change by some number. This will change by the same number. We're going to assume this change is small enough that we can ignore it. And this will be x and x. So now we set up our Kb equation to read as follows. Kb is equal to concentration of HF times concentration of OH minus all over concentration of F minus, like that. Now the Kb, again, just like in question 91, you can calculate using Kw over Ka of the conjugate acid. So the conjugate acid in this case is HF, so we'll find the Ka of HF, which is, HF has a Ka of 3.5 times 10 to the negative 4. 3.5 times 10 to the negative 4. Now we do that in our calculator. So 1 times 10 to the negative 14 divided by 3.5 times 10 to the negative 4. And we get a Kb of 2.86 times 10 to the negative 11. 2.86 times 10 to the negative 11. Right, let's put in some numbers. 2.86 times 10 to the negative 11 is equal to x squared all over 6.634 times 10 to the negative 4. Now we just have to multiply across and then square root it. So 2.86 times 10 to the negative 11 times 6.634 times 10 to the negative 4, and then we'll square root that, and that'll get me the concentration of HF and OH minus. Okay, here we go. There's the 2.86, so multiply that by 6.634 to the negative 4, and then we'll square root that. Get 1.376, 1.38 times 10 to the negative 7. 1.38 times 10 to the negative 7. That's equal to x. And this is the concentration of the HF and the concentration of OH minus. Now the question is asking us to find the pH, but we don't have the concentration of hydronium, so the easiest way to do that is simply to calculate the pOH first. So pOH is negative log concentration of OH. So we get the following. Log that, so that's 6.86. And then the pH ends up being 14 minus that. That will be 7.14. 7 pH. Right, so with this particular question, we needed two rice tables. The first rice table allows you to calculate how much, and I'll highlight this in a different color, how much F minus you have, because F minus has the ability to react with water to create a basic solution, because F minus is the conjugate base of a weak acid. Okay, so that's what we do with that first bit of information. All right, last one.
Okay, so question 93 is very similar to 92, but this time, rather than giving you the KSP, it gives you the pH. So we're going to work backwards. We're going to start at the pH, use the pH to find POH, use POH to find down. So we're going to start from pH, we're going to find POH. From there, we're going to find the concentration of OH minus, and from that, we're going to find the concentration of C2O4, 2 minus, and from that, we'll find the KSP of NaC2O4. All right, let's get started. So the pH, it tells us, is 8.82. So from here, we can then calculate POH, because POH is just 14 minus 8.82. And that gives us an answer of 5.18, I think. Yes, 5.18. Right, now we can calculate the concentration of hydroxide. And you might wonder, why are we calculating the concentration of hydroxide? Well, I'll let you in on that in a moment. So the concentration of that is going to be 5.18 negative to the power of 10. So concentration of hydroxide is 6.61. So 6.61 times 10 to the negative 6. Now this concentration is important because if you recall from our question 92, we had a equilibrium expression where we had the conjugate base, and this would react with water to create in this case HC2O4 minus, and then OH minus, like that. Okay. So we're kind of filling in our rice table a little bit backwards because the pH allows us to know what the equilibrium concentration is. So this is going to be 6.61 times 10 to the negative 6. This will be 6.61 times 10 to the negative 6. This is 0, this is 0. This would have been a plus x, a plus x. This is a minus x, but it doesn't actually matter because the change is going to be so small that whatever the original concentration is will remain the original concentration. Okay. Now we'll set up our KB because what we want is this. We want that. Why do we want that? Because in the rice table immediately after this, the rice table immediately after this will look like this. The Na2C2O4 will dissociate into the following: 2Na plus C2O4 2 minus. This will be an equilibrium because it tells us it's a KSP. And in order to calculate the KSP, we are going to need the concentration of C2O4. So we're going to need this amount, and we're going to need this amount, and this amount doesn't matter because that's solid. Okay, so what we're going to do is we're going to, from our weak base equilibrium, we're going to calculate this value here, and that value we can then slide into here, which will give us this value by, because if I fill in the table, this would have been 0, 0, plus 2x plus x, right? And then from these two values, we can then calculate the KSP because according to this equilibrium table, KSP is just going to be concentration of sodium squared times concentration of C2O4 2 minus, like that. Right. So a lot of work ahead of us. But we've already filled out at least the first rice table, and now we just have to find what is the KB. So KB again is KW over KA. So C2O4 minus is somewhere down here. There's C2O4 minus, or C2O4 2 minus. Its conjugate acid has a Ka of 6.4 times 10 to the negative 5. So Kw 1.0 times 10 to the negative 14
6.2 times 10 to the negative, wait, is that 6.2 or 6.4? 6.4, my mistake. 6.4 times 10 to the negative 5 equals 1 divided by 6.4, so 0.156. 0.156 times 10 to the negative 9, so 1.56 times 10 to the negative 10. All right, here's our KB. According to our Rice table, this KB equation is going to be equal to the following. Is equal to 6.61 times 10 to the negative 6, and that will be squared because there's two of them, divided by the concentration of C2O4 minus, which I labeled here Y. All right, so then Y will be 6.61 times 10 to the negative 6, all squared, divided by 1.56 times 10 to the negative 10. Now, throwing that into our calculator, we get a concentration of C2O4 2 minus equivalent to, see now, okay, 6.61 times 6.61 divided by 1.56, we get, this will be, the first part will be 28.0, and then the exponent will be times 10 to the, let's see, 2 times negative 6, negative 12, so negative 2. So this will be 2.8 times 10 to the negative 1. There we go. All right, so now we know the concentration of C2O4 minus. We can put that into here. So 2.8 times 10 to the negative 1. The sodium is twice that, so this will be 5.6 times 10 to the negative 1. Throwing into our KSP, we now get 5.6 times 10 to the negative 1 squared. This will be 2.8 times 10 to the negative 1. And our KSP value, we'll just throw all that in. 5.6 times 5.6 times 2.8, so it'll be 87.8 times 10 to the 2 times negative 1 is negative 2, plus negative 1 will be negative 3. And simplifying that, we'll get 8.78 times 10 to the negative 2. There we go. So this one, 93 is basically 92 just going backwards. Still require 2 rice tables, but the first rice table we deal with is actually going to be the weak base rice table, and then the second rice table will be the solubility rice table. Okay. All right, hopefully that makes sense, and again, if you guys have any further questions, do let me know.